So welcome everyone. Today we are going to talk about the progress of the European Commission-funded ECO-Qube project. My name is Çağatay Yilmaz. I'm working at Rice Research Institutes of Sweden, and I work pretty much about sustainable digitalization. And my colleague Ender is here. You can introduce yourself.
I'm Demirel. I'm the founder of DSTECH, Design and Simulation Technologies. So at DSTECH, we are focusing on the CFD simulations of thermal simulations of air and liquid-cooled IT equipment, as well as thermal simulations of data centers.
Thank you, Ender. So yes, we will start talking about cooling. I know that it conflicts with the title a bit, but we know that actually cooling and the performance and efficiency of the IT devices, they are totally correlated. So the other day, I was reading an article, and it was about the last ice age. And there was a significant detail about this. I heard that in an average, in the last ice age, the temperatures were only 47 degrees Celsius lower than today's average temperatures. So I was thinking, hey, it shouldn't be right? Like only 4 degrees. Then I remembered, okay, most of the data center owners, just to be on the safe side, they are actually lowering their cold aisle set points. And basically, this is, again, from my experience, something around 4 degrees. So 4 degrees is a significant amount. So are we overcooling? Or in the big picture, if we see the big picture, if we can actually modify in a controlled way, control the cold aisle temperatures, can we actually achieve better efficiency for the data centers in the future? So yeah, the main question is, are we overcooling, and how we are improving the efficiency of our data centers? So for us, there are two kinds of cooling. One of them is the traditional cooling, where we cool down the environment. In the most efficient case, like we list in the presentations, there are cold aisle containments or hot aisle containments. We are trying to not to separate hot and cold air, and we are trying to improve the overall efficiency. That works fine. It worked for years so far, and we are happy with this. But we are trying to introduce a paradigm shift to the market with the ECO-Qube project, where we focus on the compute element. The main question is, if we listen to the data center a bit better, if we really listen, pay attention on how it's performing, can we turn this system into something better? So the traditional system, you all know this schematic from ASHRAE. This is a great tool. I love it, and we still rely on this tool. So in this system, what we do, as discussed, we cool down the environment. So the ASHRAE standards shows us, and the IT systems manufacturers, they say, okay, you have to cool our devices within the recommended envelope, or A1, A2, so we just follow the instructions. Because we know that if we do so, we both guarantee the performance of the IT devices, and we also guarantee the overall efficiency. However, what we are trying to do in the ECO-Qube project, we try to listen the IT devices itself. Yes, this schematic is from a Raspberry Pi. This is not a traditional IT system that you are working with. But the main idea is the same. So I deliberately put this picture because there are no fans. There is nothing that can disturb us. And we can clearly see the thermal effect. And the thermal throttling on the IT devices. So what we said, we want to maintain the performance, but meanwhile, we are trying to optimize the efficiency. So on the second picture, we discussed a lot how we can do this, how we can achieve this, maximize the performance and efficiency. So in this system, we go back to the environment cooling, and we have our standards. And in these standards, what we do, I'm talking about the air cooling systems right now. we make sure that cold air is flowing through the server, cooling the server. So how we listen all the servers all together and make sure they are sufficiently cooled? This is a bit tricky because it looks like, hey, you are taking a shower and you have a desired temperature, and this desired temperature you also have a desired water flow. And you have two knobs, a cold knob and a hot knob. So how you optimize the angles of these two knobs and make sure that you get the right flow and the right temperature. And meanwhile doing that, if you consider that there are hundreds of servers in a data center, in the big picture, how you make sure that all individual server is receiving the right amount of the coolant for the optimum operations. This is the engineering problem that we were facing. Okay, this is the background history. Now my colleague Ender is going to deep dive into engineering side. Ender, floor is up, yours. Couldn't get it, yeah.
Okay, thank you. In order to minimize IT and cooling energy consumption in data centers, we developed some tools such as ECO-Server Power, ECO-FTE, ECO-EAWO, and ECO-Dynacool in the scope of ECO-Qube project. ECO-Server Power is developed for the prediction of the power consumption of OCP servers, which is very important for the optimization of workloads inside the data center. The thermal prediction or thermal side is an important parameter because there is a strong interaction between temperature distribution and power consumption of servers. So the fast estimation of the CPU temperatures and outlet temperatures in a data center, we developed ECO-FTE tool. ECO-EAWO utilizes ECO-Server Power and ECO-FTE for the minimization of IT energy consumption to optimize the workload distribution inside the data center. And finally, ECO-Dynacool optimizes the cooling parameters such as fan speed and valve opening ratio, which is very important in EMPA data center, which is one of the pilot sites in ECO-Qube project. So I will give a brief information about these tools. ECO-Server Power has been developed for the Leopard version 2 OCP server, which was deployed in EMPA data center in Switzerland. So the power consumption of the server consists of the IT power consumption and the fan power consumption. So the IT power consumption can be classified as the idle CPU dynamic pressure, power consumption and the leakage power consumption, which is connected with the CPU temperatures. In order to understand the IT power consumption inside the data center, we carried out experimental studies using different server utilization ratios and fan speeds. So, and we have seen that the hyperthreading is a very significant parameter for the power consumption of the server, because a sudden drop has been observed when the utilization rate exceeds 0.5. So based on the experimental studies, we proposed an empirical equation and a partial empirical equation, which is valid below 0.5 and which is greater than 0.5. So this equation can be used reliably for the estimation of the power consumption for a given workload and fan speed in this system. So we conducted additional experimental studies in order to test the accuracy of this equation, and we have seen that this equation can be used reliably for the optimization of the workloads. So in EMPA data center, 24 OCP servers are deployed. So in order to estimate the CPU temperatures, CPU temperature is a very important parameter for our algorithms because we optimize the workloads depending on the CPU temperatures, looking at the CPU temperatures, keeping them below the threshold values instead of inlet temperatures. So we performed a series of numerical simulations for the estimation of the thermal side. Then we created some matrices, and for a given workload and cooling environment, So this ECO-FTE algorithm can predict the CPU temperatures below 1 second for a given workload and cooling environment. So we assess the performance of this algorithm using experimental studies. Experimental studies were conducted in EMPA data center. So the predicted and collected values were compared. As we can see in the figure, the FTE algorithm can predict CPU temperatures accurately with the IPMI data. The EAWO tool uses ECO-FTE and ECO-server power for the optimization of the workloads for a given workload inside the data center. So we performed numerical and experimental studies for the demonstration of the impact of these tools in the relevant environment. During the numerical studies, different kinds of optimization algorithms were used, such as the randomly distributed population algorithm, particle swarm optimization, and genetic algorithm. And we have seen that the randomly distributed population algorithm is superior to other numerical methods. So we selected this algorithm during the experimental studies. We conducted experimental studies using some dummy loads created by OpenFOAM using Slurm job submission algorithm. And we conducted 4 experimental tests, and we compared the results of ECO-EAWO with the conventional workload distribution algorithm. And we have seen that the IT energy consumption can be reduced by up to 15% when ECO-EAWO tool is used for the optimization of the workloads inside the data center. So here is the architecture of ECO-EAWO. As Çağatay mentioned, we have to listen to the data center, so there is a strong interaction between our tools and Prometheus to collect the thermal data from the system. Then, when a new task is submitted to the data center, ECO-EAWO distributes the workloads in a way to reduce the power consumption inside the data center. Then, as we mentioned later, the Kubernetes system can automatize this system in the near future. The second tool is the ECO-Qube, which focuses on the minimization of cooling power consumption in a data center. This is the schematic figure of cooling system in EMPA data center. We have to minimize the power consumption of the cooling system by optimizing the fan speed of the cooling system and valve opening ratio, which adjusts the flow rate passing through the heat exchanger because heat is removed from air using this heat exchanger. So we need to reduce the heat load sent to the chiller, which is located outside of the building. So the cooling parameters, the optimization parameters are valve opening ratio and inverter fan speed. So our constraint is the CPU temperature should be kept below 80 degrees Celsius, which is available for this type of server model. Our objective function is the power consumption of the total power consumption of the cooling system. We developed an optimization algorithm in here. Depending on these constraints, the cooling system's parameters are optimized. We compared the default and the current cooling system's behavior with the developed algorithm, ECO-Qube. The ECO-Qube can optimize the cooling parameters in a smooth way in comparison to the default algorithm, because the default algorithm can open and close the valves of the cooling system in order to set desired supply temperatures. Our algorithm can predict the CPU temperatures in an accurate way, so the cooling parameters can be optimized depending on these values. Then we compared the power consumption of the cooling system with the conventional, with the current cooling system in EMPA data center, and we have seen that the EcoDynaCool can reduce cooling power consumption by up to 35% in comparison to conventional or current cooling system. As Çağatay mentioned in the beginning of the presentation, instead of focusing on the inlet temperatures inside the data center, our chip temperature-based algorithm can keep the CPU temperatures below the threshold value. So by increasing the inlet temperatures about 28 or 29 degrees Celsius, these energy savings can be gained. So this is a very critical parameter. So we monitored the CPU temperatures during experimental studies, and because of the accuracy of the numerical model and experimental studies, the CPU temperatures were observed about 78 or 79 degrees Celsius, which is so close to the threshold value. Okay, this is your side.
Yes, I wish our DevOps engineer Oğuzhan was here today, but he couldn't make it. Visa issues. What I can say, like the challenging part, all we discussed here, it's a research project funded by European Commission. So the next question is how we are actually carrying this dedicated important work into real life environments. So one of the biggest obstacles in front of us is still relying on open source technologies and make it globally available. So obviously we use Kubernetes as our main medium, and we have chosen, instead of developing like really heavy middleware applications, we decided to train Kubernetes. So our Kubernetes, instead of standard Kubernetes scheduler, it is not only allocating the loads randomly as it does, all the tools that we already discussed, they are step-by-step being integrated into the new Kubernetes scheduler. So what the system does, there is a continuous loop. So whenever there is a change on the IT load, the system asks the IT device itself, all the IT devices itself, hey, what is the current status? And cooling, hey, what is your current status? And basically, altogether, this system smartly allocates the workloads, plus controls the coolant side as a promise of a holistic coolant system in the data centers, which optimizes both hardware and software elements of the data centers. So the whole presentation that we discussed today is actually just focusing on the data center side. But what EU is trying to do on the way to climate neutrality, this is a grid integration problem. This is a problem that we need to optimize. Yes, the data center itself, then to integrate it into the grids and energy systems in the most efficient way. So unfortunately, we don't have time to cover all the project scopes and goals, but what we are doing is going to be compatible with the new EU regulations, and we're going to be discussing about it during the next presentation. So I would kindly remind you to stay with us to hear more about the new EU regulations, especially the Energy Efficiency Directive. So main takeaways of this presentation, yes, listening data centers and IT elements like compute elements makes a difference. And if you listen it well, the minimum energy gains is around 15% on the IT side. However, if you combine this IT efficiency, and if you have a holistic methodology and combine it with the hardware of the system components, especially the cooling, you can your systems can, instead of cooling the environment, they can understand the cooling requirements of the IT equipment and optimize the cooling efficiency as well. And our systems, as Ender just mentioned, smartly increased the inlet temperatures in our initial studies around 4%, and this 4% was equal to 35% in efficiency gains on the coolant side. What I'm trying to say, this is a great potential, and such research has to be continued to take these technologies and adapt them into real-life data center environments. And our call to action, yes, follow up ECO-Qube project. We are in the last 6 months of the project, so from now on you will hear more about our findings. Follow EU Code of Conduct data centers, where you can find the latest trends and information about the data centers efficiency. And as discussed, join our next session, where we will discuss the overall feature of the data centers energy efficiency. So thank you for coming.
Thank you, Çağatay and Ender. Great presentation. Any questions?
Oh.
I used to work with them as well. Great to see some results. Okay, so the first question will be like, what you see is with ECO-Dynamical that if you raise the inlet temperature, that the power consumption goes down. Have you tried to increase that inlet temperature as well and see what's the difference then? Like if you have now you also had a difference in inlet temperature, but what if you forced the system to have that higher inlet temperature? What's the reduction that you get then?
Okay, I will leave it to you, but I think our system boundaries here was the CPU temperatures, because we don't want to burn them. So continuously tracking, actually, you know it, but continuously tracking the CPU temperature let us safely increase the CPU temperatures. Meanwhile, the smart workload allocation in the data center is making us sure that there is no hotspots in the data center. So it's like try to avoid hotspots before they happen, right? This was the main motivation when we started the project. Do you want to add something?
Our first constraint was the CPU temperature, so we tried to keep this value close to the threshold value. So when we observe the inlet temperatures, we have just noticed that the inlet temperatures has increased the standard values or suggested values by ASHRAE standard, for example. This increasing has provided a gain in energy saving in ECO-Qube project.
Can you go back to the utilization of the power slide, please?
ECO-server power, maybe.
ECO-server power.
Yeah.
Was it on the?
Further back.
It should be back, yeah. Yeah. One more slide.
One more? This one?
Yeah.
That one, yeah. Does this take into account the change in behavior and relationship between server power and server utilization when you modify the BIOS from power efficiency mode to performance mode?
No, because we didn't want to modify anything, especially on the BIOS.
Which is this in then?
Pardon me?
Which BIOS setting is this in?
I wish Oğuzhan was here. I need to get it with an email because, visa issues.
Oğuzhan was provided this service to us for the controlling of fan speeds and utilization rates. So he knows the details. He's not here, unfortunately.
And just a quick second one. On the next slide, the power model that you've got there only incorporates CPU and temperature. So I assume your workload is a CPU-heavy workload. Is there any plans to incorporate memory stressing workloads or storage stressing workloads into your power model?
It's a great question. This is one of our limitations because so far in this research project, we have to focus on the CPU-intensive workloads, not memory or not the GPU-intensive workloads are not studied in this particular study. But this is one of the limitations and we have to work on it in the future.
We should talk after this.
Yeah, sure.
Okay. Thank you.
To ask a question then, yeah.
And I'm scared now.
Okay, so getting things straight. So you're not altering the fan speed. You're letting the BIOS change the fan speed.
Yes.
Because if you remember the Bowden type project that we ran at RISE, we took control of the fans. So the issue here is obviously when you're running at 80 degrees centigrade, your fans have slowed down quite a lot. So you're trading current leakage or wasted energy through the CPU, if you like, heat generation, with the fan energy dropping. That's how I understand it first, but that's a statement first. But the question I have really is on the 35%, does that take into consideration the cooling outside of the rack? and are you just focusing on the reduction in energy consumption in just the cooling infrastructure, the fans and the downstream cooling in the rack?
Yeah, brilliant question, but the answer relies on what EU wanted us to do in this project call. So it was a like data center integration into a building. So what we considered about the cooling power consumption is our load that we send to the chillers. So we didn't actually consider like basically the whole cooling system's efficiency, because we are a small piece of the puzzle in the equation. So
this is the rack
our
level.
boundaries are just in between this micro data center.
Okay, yeah. Because really, the optimal thing about efficiency really is the workload that you're doing for the energy you're consuming. So, and I can go on about this, but maybe we'll talk about this in the next session. Yeah.
Maybe I can welcome you to the stage too.
Well, thank you all. Thanks, Çağatay, and
Thank you.
good presentation.